We will finish off with a good one. Here's kind of leaning deeper into the applications of arc length. This one is find the area round to 2 decimal places. And you notice the shape that's provided for us. We'll try to find that area of that curved, it's almost like a curved plate. So it begins, kind of curving along this circle part way, and then it extends back. And I think this should be curved a little bit more because it should have the same curvature as the front part of that. You get the idea. Okay, we've got this curved kind of plate. Maybe it would be like the cover kind of seal something. I don't know. We want to find the area there. You think, well, find the area. How does this connect to arc length? Okay, so what we want to notice is we want to find the arc length around the circle. And once we have that length, then we just need to multiply by, almost like the width. And that would give us our area. So area here will be 3 times the arc length. By the way, it's got 3 feet. I think we're thinking of all of these units as being in feet. Never mind the scaling. Okay, so once we have that arc length, if we multiply it by 3, then we'll get the area. Okay. So, how to find the arc length? Well, this problem, they don't give us a function, right? We've got to come up with the function on our own. And that can be, a big challenge for students. How are we going to come up with a function to describe that arc? Well, it's on a circle. So let's get the equation of that circle. So if you remember the equation of a circle here, this one is centered at the origin. It's got a radius of 4. This is 4 as well. It's 4 all the way around. So the equation of that circle would be x squared plus y squared equals 16. Okay. Think, okay, well, we're off to a really good start with that, but we don't have a function yet. So what we're going to do is take the equation of our circle and solve it for y. If you solve for y, let's see, subtract square root, you'll get the square root of 16 minus x squared. Now, some of you might be thinking, wait a second, I've got an objection. Shouldn't it be plus or minus the square root of 16 minus x squared? Because when you square root, you got to put a plus or minus in front. Yes, you should. But I'm saying only consider the positive square root. If we only consider the positive, that's the upper half of the circle. So actually, this function describes just the top half, like so. The negative square root would describe the bottom half of the circle. You think, well, how can we get away with only looking at the top half of the circle? Because part of it's down here. That's true. What we're going to end up doing is finding the arc length of just the upper half here and then multiplying it by 2, since it's nice and symmetrical. Okay. So that will come, that'll kind of flesh itself out when we set up the integral. Let's for now go ahead and, if that's our function, let's take the derivative. So y prime, well, let's see, so that'd be 1/2 16 minus x squared to the negative 1/2 times negative 2x. And if we clean this up, right, 1/2 and 2 cancel nicely. And I'm going to go ahead and write it as a fraction. I really prefer it in this style since we're about to square. So I'll put the negative x on top, and then underneath, let's go with square root 16 minus x squared, so that when we square, we really see it come out nice and neat, and it's going to be easier to work with this fraction later as well. So squaring the negative x, well, that turns into a positive x squared. And then, of course, the square root just cancels. So x squared over 16 minus x squared. Okay. Now we can set up our integral. So we remember that it's 3 times the arc length. So the area here 3 times. I'll mention the 2 here in a moment. So we've got the integral from 1 to 4, square root 1 plus, and there's our y prime squared, x squared over 16 minus x squared dx. Now you can see my notes. So this integral only describes the upper half of our plate. So then we need to multiply it by 2. So what we're doing, I don't think I can get it all on the screen, but we're finding this right here. And we can see the x values go from 1 to 4 right there. And then we're just going to double that to get the full thing. And then, of course, multiply it all by 3. So here it is again. Once we have the integral set up, well, now it's a matter of actually executing it. And turns out this particular one will need one of our new techniques. So let's see how that plays out. Kind of keep that there. The first step, we're going to simplify what we see under that square root. And that's really a theme with these problems, that they typically begin by trying to simplify what's inside that. Well, in this case, this one's different from the others. We're not going to factor something out. In this case, we're going to find a common denominator. So it's kind of nice. We have the 1, so that would be 16 minus x squared over 16 minus x squared. So when we combine them, we'd have 16 minus x squared plus the x squared, and that's all over the denominator 16 minus x squared. And you notice I'm just going to clean up the 3 times 2, and we've got our integral, and okay. Now this is really great, and you see it right away. Negative x squared plus x squared is gone. And we can even take the square root of the 16. So square root 16 being 4, we can pull that 4 all the way out in front. Simplify it with the 6. And okay, here we are. So the 1 on top is fine. We'll still have the square root. It's like we're taking the square root of top and bottom separately. So square root 16, and then that comes out. So, and then the square root of the denominator, 16 minus x squared. Okay, once it's all simplified down as far as we can go, then we think, okay, are we able to just take the integral, or are we going to need some kind of a special technique for this? And well, we can't just knock out this antiderivative right here. We need a technique. Which integration technique would apply in this situation? And if you answered a trig substitution, you nailed it. Yep, we see the square root, we see those perfect squares, and that it's in a fraction is pretty common for these. Okay. So here we go. I'm not going to spend a whole lot of time breaking this down since it's from the last chapter, but all right, I'll make my right triangle. Since we're subtracting, that needs to go on one of the legs. The 4 would go on the hypotenuse and the x on the other leg to make it all fit, the Pythagorean theorem. And then looking at my triangle, I can see that the sine of theta would be square root 16 minus x squared over 4. So if I multiply the 4 over, then I can say 4 sine theta equals that square root. I also notice that cosine theta is x over 4, so I can multiply that 4 over and say 4 cosine theta equals x. Now the truth is I don't really need the x for my integral, but I do need it to help me get dx. So taking differentials here, negative 4 sine theta d theta would equal dx, and we've got a replacement for our denominator in our dx. Okay, plugging those in, this one's actually going to come out pretty clean. So denominator 4 sine theta, and the dx negative 4 sine theta d theta with all the other stuff there. This is great because look at all that amazing cancellation, and we'll go ahead and pull the negative all the way out in front. All we have is area equals negative 24 integral from 1 to 4 d theta. So of course that integral is simply theta from 1 to 4. Now I'm writing from 1 to 4, but remember these are values of x. We need to replace the theta before we plug these numbers in. How can we replace the theta in this case? Well, if we go back a little bit, we said 4 cosine theta equals x. So that means cosine theta equals x over 4. So theta would equal arc cosine x over 4. So we have negative 24 arc cosine or inverse cosine x over 4. Now we can evaluate from 1 to 4. So plugging in, I'll just leave that negative 24 in front. Plugging 4 in for x, it'd be the inverse cosine of 1. Turns out that is 0. Minus inverse cosine of 1/4. This is not a nice answer, so I kind of prefer to write it this way for the moment. But now I'm going to grab my calculator and multiply that. The answer does come out to be positive, which is a good thing. We got the area to be 31.63, and if you're wondering the units, in this case it's all in feet, so that's feet squared. And there we are. Well, that is it for 8.1. Just sort of the last thing, maybe to kind of close this, you're going to see a few patterns in the problems that you do. So, here's where we began. Here's the first example we did together, right? So, you'll see these kind of the same styles in a lot of the problems they present, because it turns out in order to do these arc length integrals, the numbers just kind of have to fit together nicely. So the fact here, when we took a derivative, you notice that we ended up with x to the third minus x to the negative 3, right? One was positive, one was negative, so that when we squared it, it worked out a certain way, so that when we factored and combined again, we got the same thing but with a plus, right? That wasn't a coincidence, right? You compare here to here. So that's kind of a theme you'll see with some of these questions, right? Just the numbers just have to click together. Another theme in the next one, right? So it's not that anything really all that special with the numbers here. It was the fact that when we took a derivative, we got a 1/2 power, so that when we squared, it went away. So that was really nice. And then in the last one that we just saw, when we set up the integral, we had this situation, so that when we did a common denominator there, it actually worked out and simplified really well. So you'll see some other things in the homework as well, but you'll definitely see these 3 themes that came up here in our lecture examples come back up again, simply because in order to take integrals like this with that square root, right, nice things kind of have to fit together. Okay, that's it for 8.1.